Welcome to The Explainer. Today, we're tackling something that absolutely dominates the headlines and runs our digital world: neural networks. But listen, we're not going to talk about them as these mysterious, magical buzzwords. Instead, we're going to break them down into what they actually are at their core: beautifully structured mathematical functions. If you've ever wanted to pop the hood on machine learning and actually understand the mechanics of how it works, you are in exactly the right place. Okay, let's dive into this. Here's our roadmap for today. We'll be hitting 1. The recognition challenge, 2. Neurons and architecture, 3. Hidden layers, 4. Weights and biases, 5. Simplifying with matrix notation, and 6. Sigmoid versus RELU. Starting off with section 1, the recognition challenge. Think about a sloppily written number 3. Your brain has absolutely no trouble recognizing it, right? Even if the lighting is weird or the handwriting is terrible, your visual cortex just effortlessly figures it out. But if I told you to sit down and write a traditional computer program to take a raw grid of pixels and output what digit it thinks it's looking at, suddenly a task that's comically easy for a human becomes a complete nightmare for a programmer. And this perfectly illustrates the scale of our starting point. The low-resolution images we're dealing with are basically a 28 by 28 grid of pixels. You multiply that out, and you get 784 individual pixels. That number, 784, is the absolute bedrock of the network we're about to build. It is our raw data. That brings us to section 2, neurons and architecture. When I say the word neuron, honestly, forget the biology textbook for a second. In our network, just think of a neuron as a tiny container holding a single number between 0 and 1. That's literally it. So for our 784 pixels, we have 784 of these containers. A neuron holding a 0 represents a completely black pixel, and a 1 represents a completely white pixel. Now, the specific number sitting inside that container is called its activation. You can visualize this like a light bulb. If a neuron's activation is a high number, close to 1, that neuron is lit up. And it's this lit up activation that actually triggers the flow of information forward into the rest of the network. So let's map out the actual layout of a basic, plain vanilla network. We start with our input layer of 784 neurons. Those are our raw pixels. Over on the far right, we have an output layer of 10 neurons, representing the digits 0 through 9. Whichever output neuron shines the brightest at the end is the network's final guess. But sitting right in the middle, we have 2 layers of 16 neurons each. These are the hidden layers, and frankly, right now they're a giant question mark. How on earth do 784 pixels filter down to 16 neurons and then spit out a correct answer? To answer that, let's jump into section 3, hidden layers, and look at the theoretical purpose of those middle layers. Here is how this builds conceptually. Think about how you recognize a 9. You see a loop on top and a straight line on the right, right? An 8 is just 2 loops. So in a perfect world, our network is building these abstractions step by step. Layer 1 takes the raw pixels. Layer 2 combines those pixels to recognize little edges. Layer 3 takes those little edges and combines them into loops and lines. And then that final layer puts those loops and lines together to recognize the final digits. We are taking the incredibly complex visual of a number and breaking it down into bite-sized, recognizable subcomponents. Which leads perfectly into section 4, weights and biases. Because mechanically, how do we tune this network to actually look for those specific little edges? This is where we bring in weights. A weight is just a number representing the connection strength between a neuron in one layer and the next. Picture them as little dials and knobs. What we're doing is computing a weighted sum of the pixel values. If we want a neuron to hunt for an edge in a very specific spot, we crank up positive weights for those exact pixels, and maybe assign negative weights to the surrounding ones. Boom! The sum maxes out only when the exact pattern we're looking for is lit up. But hold on, we probably don't want that neuron firing if the weighted sum is just barely above 0. We want a strong, confident signal. Enter the bias. A bias is a number we tack on to that weighted sum to act as a threshold. Say we add a bias of -10. Well, now that weighted sum absolutely has to be greater than 10 before the neuron actually lights up and passes the message along. It's basically a threshold for meaningful activation. Now, let's talk scale, because this is where things get wild. For every single neuron in our hidden layer, there are 784 weights connecting it to the previous layer, plus a bias. Add up all the connections across this entire relatively simple network, and you get almost exactly 13,000 weights and biases. That is 13,000 individual knobs and dials dictating exactly how this network behaves. Because hand-tuning 13,000 dials sounds like absolute torture, we rely on Section 5, simplifying with matrix notation. To manage all this crazy complexity, we stopped thinking about individual connections and pivot to abstract math, specifically linear algebra. We take all the activations from one layer and neatly stack them into a column, called a vector. We organize all those thousands of weights into a tidy grid, called a matrix. And the biases? They become another vector. And this is the magic of math right here. All of that messy, overwhelming complexity gets condensed into one neat little expression. The new activations equal the weight matrix multiplied by the old activations plus the bias vector, all wrapped up in a squish function. And this isn't just to make it pretty for humans to look at. Computing matrix vector multiplication is something modern computer libraries can crunch insanely fast. Finally, let's talk about that squish step in the formula, with Section 6, Sigmoid versus RELU. Back in the day, networks relied on something called a sigmoid function. It's this smooth curve that takes any number and squishes it into a value between 0 and 1, kind of mimicking a biological neuron turning on or off. But today, the industry has heavily pivoted to RELU, the rectified linear unit. And RELU is brutally simple. It just takes the maximum of 0 and your input. Input is negative, it outputs 0. Input is positive, it just passes the exact number right through. No fancy curving required. To give you some context on this, deep learning expert Leisha Lee noted that using sigmoids actually made deep networks really difficult to train. People basically just threw RELU at the problem, this incredibly simple threshold identity function, and it just happened to work flawlessly. Sometimes ditching the complex biological analogies and just using simpler math makes the whole machine learning process vastly more efficient. So pulling back from the matrices and the 13,000 parameters for a second, we reach this really cool realization. This entire neural network, all the pixels, the hidden layers, the edges, the weights, the biases, is ultimately just one absurdly complicated mathematical function. You feed it 784 numbers as an input, and it spits out 10 numbers as an output. And honestly, it's kind of reassuring that it looks this complicated. Because if it were simpler, it wouldn't have the sheer power required to recognize human handwriting. Which leaves us with one massive cliffhanger. We've got the physical structure down. We know there are 13,000 dials just waiting to be perfectly tuned to find edges and loops. But how does a computer actually figure out the right settings on its own? How does a network learn to perfectly set 13,000 parameters just by looking at training data? Well, that is the actual magic of machine learning, and a perfect question for you to chew on as you continue your journey into this topic. Thanks for joining me on this explainer, and keep exploring.